one of the subtopics that we need to discuss when we're talking about equilibrium is something called a solubility product equilibria, or KSP for short. That's equilibria with solubility in mind. So before we really get launched in talking about this form of equilibrium, I think it's important that we review some topics about solubility. So first, a bit of a solubility review. Some general topics, some general terms that you should already be familiar with are something simple, like solute, solvent, and solution. Just as a reminder, a solute is the material that we'll put into a solution that is dissolved. A solvent is usually the liquid material that is doing the dissolving, and when we put the two together, they create a solution. I also want to take this opportunity to review how substances actually dissolve. Now, for ionic substances, this has everything to do with an ion-dipole interaction. Remember that ionic substances are generally in these weird things called crystal lattices. Now, that's an interaction between the positive and the negative ions, forming this beautiful crystal structure. When a polar compound such as water comes near it, they also have their own little intermolecular force, that polarity, that separation between a positive side and a negative side. Well, they start to interact with those ions, and then they can actually disrupt the crystal lattice form. Now, what you're seeing in this image here is that the water molecules have wrapped themselves around these ions and have effectively pulled them away from the crystal lattice. The negative ion here you can see has been wrapped by the positive or red hydrogen atoms of the water molecules, and it creates this little water shield around this ion and pulls it away into the solution. The positive ions have in fact been wrapped around by the negative oxygen side of the polar water molecule. And again, this is called an ion-dipole interaction. So it just keeps happening over and over again that these ions get pulled off of this crystal lattice until essentially your crystal lattice is all gone. So the ionic substance will essentially break down from something that we see as being solid into something that is essentially just ions floating around in water. And this is what it means for an ionic substance to be completely soluble. Now, although we do know that some covalent compounds can also dissolve in water, by the rule like dissolves like, so polar substances will dissolve in polar solvents, nonpolar substances will dissolve in nonpolar solvents. We're not really going to be considering them in the case of this form of equilibrium. We're going to limit our scope to just the ionic compounds. But again, just to take a moment to review what that actually looks like, on the left-hand side of the screen, you can see an ionic crystal lattice being dissolved by the polar water through ion-dipole interactions. Whereas on the right-hand side of the screen, you're seeing a polar material being dissolved by the similar polar water through these weird dipole-dipole interactions. You can see clearly that the positive hydrogen atoms are attracted to the negative part of that little blue molecule, and that the negative water molecules are attracted to the positive end of the blue molecule. That's again called dipole-dipole interactions. It still creates that same water shield, pulling the molecules off of the covalent crystal lattice and off and into the water. So let's go one step further now and really get to kind of the AP side of this whole thing. So far, what we have been taught, when we're taking a look at whether or not something can dissolve, we usually have the solubility rules right in front of us. And we've learned that anything that's marked as being AQ is soluble and will dissociate or rip itself apart into those two ions to 100%. Whereas anything that's been marked as solid or being insoluble will not dissociate. In fact, it dissociates to 0%. Well, unfortunately, usually in Year 1 chemistry, we do teach you these things in this form of black and white, just so you can kind of learn the rules of the road. And I think we've seen several times so far that in chemistry, things don't tend to be that black and white, that there's further explanation, and AP starts to layer in that explanation. This is another one of those instances where we may have oversimplified the 0% part of this. In fact, actually, everything dissolves to a small percentage. Nothing really dissolves to 0%. It's equilibrium that's going to help us figure out what percentage to which it actually dissolves. So let's really dig into this. So really, let's get rid of that 0. Let's just consider this as we don't really know what the percentage is, but it is under 100%. So we need to redefine some terms now. Instead of just saying soluble and insoluble, we also need to say slightly soluble. And luckily, these numbers have actually been quantified for us. So soluble for right now is going to be referring to any solution that can actually dissolve up to at least a 0.1 molar solution. Insoluble is going to be anything that can dissolve, but only to a limit of 1/10,000th molar solution. Slightly soluble is going to be somewhere in between those two numbers. So my goodness, why don't we take a look more at something even more chemistry related here? I want to kind of show you the equation part of this. Let's focus first on the dissociating to 100%. We can write out an equation for something familiar, such as NaCl dissolving in water. Notice that water does not appear in the equation. It's kind of taken with a grain of salt, yes, pun intended, that when we write down AQ, that the water is present in that system. So here we would have aqueous NaCl dissociating or breaking apart up into the Na1 plus and the Cl1 minus. And that again happens to 100%. This style of equation is known as a dissociation equation, and it essentially shows you how that compound is going to handle itself once it hits that water. The Na and the Cl will effectively break apart into their own entities. Now, we can write that for a plethora of different things. Again, anything that's going to be marked as being AQ will do this to 100%. But that doesn't necessarily mean that we can't write one for something that dissociates to less than 100%. Let's take, for example, the insoluble compound CaCO3 or calcium carbonate. We can write a dissociation equation for it as well, but notice now that there's two major differences on the inside of this equation. First of all, the NaCl equation that dissociates to 100%, I very purposefully used a single-headed arrow here. This is essentially a one-way street. I would have to take the water back out in order to actually get the salt back out of my solution. So I like to use this single-headed arrow here, indicating that this is extremely and highly soluble. Whereas with the calcium carbonate that is not so highly soluble, I'm using on purpose a double-headed arrow, implying that this is an equilibrium scenario. We may have reached equilibrium between its solid material and its dissolved material, but still it's an equilibrium and it's less than that 100% that NaCl will go to. Second major difference, NaCl. I'm using very specifically the state symbol AQ. And again, anytime I use that state symbol AQ, I want to use the single-headed arrow. Whereas with the calcium carbonate, I'm very specifically using the state symbol solid, and that's again used with a double-headed arrow. Now, just as we've seen before, when I use these two different types of arrows, it makes a very stunning implication, and that is, in fact, that we're going to have two different styles of math here. Generally speaking, when we're using the single-headed arrow, I can use stoichiometry, whereas when I have a double-headed arrow, I have to use that new equilibrium style of math through equilibrium expressions. So let's take a look and see at least a little bit about how this is going to kind of play out as we move forward with talking about concentrations and percentages and all of those wonderful things. First, let's focus on the 100% soluble solutions. So again, anything that's marked as being AQ is 100% soluble. We use a single-headed arrow, and that implies that I'm able to use stoichiometry. Thank goodness that's something I can wrap my head around. So if I'm told that I make a solution that's 0.75 molar in NaCl, what that implies is that 100% of that 0.75 molar solution is going to dissociate. So I'd really like to know what the concentrations of the ions are on the other side. Well, if it's a 1-to-1 molar ratio between NaCl and Na, and between NaCl and Cl, then I can assume that both of those solutions at the other end are also going to maintain that 0.75 molar. Now, just so you can kind of see the stoichiometry of it, let's take a look at another example. Let's say something like CaCl2. Here's the dissociation equation for calcium chloride, 100% soluble. And again, single-headed arrow, AQ signs all over the place. Let's say, for example, we start again with a 0.75 molar solution of calcium chloride. When that breaks apart, again, due to molar-molemole ratios, 1 mole calcium chloride makes 1 mole calcium. So I know at the end, my calcium concentration should also be 0.75 molar, but my chlorine is double that. Instead of 0.75, my chlorine concentration is instead going to be 1.50 molar. Again, the multimole ratios matter here. Just so you can kind of see that stoichiometry, if I take the starting molarity of 0.75 moles of calcium chloride to 1 liter and exchange moles of calcium chloride for moles of chlorine, you can actually see mathematically how that changes the molarity of my anion chlorine. Now let's take a look at the solutions that are not 100% soluble, say something like the calcium carbonate.